Today we're learning how to graph systems of inequalities. And just to maybe save us some confusion on this first example, I'm just going to solve each of these for y. So it's a y less than or equal to, or a y greater than or equal to. That way everything's going to look mx plus b-ish for us to start. And so when I go to graph y greater than or equal to 1/3 x minus 2, I'm going to start down at -2 and go up 1/3. And I know since that's a greater than or equal to, that's going to be a solid line. And if you remember, when we're graphing inequalities, we're doing shading, right? So I taught you that when the y is by itself, greater than, y greater than, just indicates that we're going to shade above. I'm going to actually save my shading for later, but I'm just going to make like a little indicator arrow here that reminds me that I really want to shade everything above that line. For my second line, my y-intercept is down at -5, and we're going to slant down 2/1. Another solid line. And since I got the y by itself, y less than or equal to tells me that I can shade below that line. Finally, if I graph x is greater than -4, that's my first dotted line, and x equals -4 is this vertical line that goes through x equals -4. And since it's greater than, I'm going to shade on the right side of that line. And now the question is, what got shaded all 3 times? Because that's our solution. Normally I won't have you do this, but just to demonstrate, remember our green line, we would have shaded everything above the green line. And then for the reddish line, we would have shaded everything below the reddish line. And then for that vertical line, we would have shaded everything to the right of that line. Now this would be messy if you tried to do all of this shading, but can you tell me what area of the graph got shaded all 3 times? And hopefully you're seeing that it's this little triangle's worth of area that got shaded all 3 times. And that tells me that my final answer is just the area right in here. It's still infinitely many points. Lots of different points if you consider all the decimals and everything. Lots of solutions to this system, but anything in that little region will be a solution to all 3 inequalities. A little vocabulary, that region is called the feasible region. It's the area where all the solutions are. This one's a bounded feasible region because it has borders on every side. An unbounded feasible region would just go on forever, and we'll see an example of that coming up. So to recap the basic strategy here, we're going to graph all of the inequalities, and then we're going to look for where the shading would have overlapped, and that's our solution. Let's start with x greater than or equal to 0. Here's where x is equal to 0. So I would shade everything to the right. Y greater than or equal to 0 is going to be everything above that x-axis. So already we've narrowed it down to just the first quadrant. Can you sort of see that? That the only thing that's working for everybody right now is just the first quadrant. But we still need to graph the last equation too. Let's see if we can do this one using that intercept method. If I had plugged in a 0 for y, that would make x equal to 6. So I know that the point 6, 0 is my x-intercept. Same thing for the y-intercept. If x were 0, then y would have to be 8. So the point 0, 8 is my y-intercept. And that's a quick way to just get our line down here. We've got a y-intercept. We've got an x-intercept, and this one's going to be a solid line. But since the y is not by itself, it doesn't really help us. Like, is that going to be above or below? It's hard to tell. So this is where we like to just pick an ordered pair to see which side of the line. And remember how we used to like to pick 0, 0. So if I do 4 times 0 plus 3 times 0 greater than or equal to 24, is 0 greater than or equal to 24? It is not. And that just tells me I'm not going to be shading on this side. So it looks like this is one where we would shade above the line. And what part of the graph would have been shaded every time then? It would have been only things in the first quadrant that are above the line. And can you see how this region would go on forever and ever? This is an unbounded feasible region. Again, infinitely many points would be solutions to all three of those inequalities. One more example, just to make sure you feel good about this. I'm going to graph y equal to 0. This is a greater than, and the y is by itself, so I can shade above. This second equation, I could either graph it in intercept form or solve for y. I'm kind of feeling solving for y on this one. Have to switch the signs. I'm dividing by a -4. That one's a dotted line. And then I'm kind of on this last one thinking of the line y equals x, or y equals 1x plus 0. So I'm going to start at 0, go up 1 over 1, up 1 over 1, up 1 over 1. And that one's another dotted line. Forgot to do my arrows on the second one. This one was y greater than, so I'm shading above this reddish line. So above the greenish line, above the reddish line, but then this one's below that line. I wonder if this will be the hardest part. Can you tell what part of this graph would have been shaded all 3 times? If you ever do have a hard time being able to tell, feel free to lightly shade for each line. So here's for the green line, here's for the blue line, and here's for the reddish line. If that helps you, that would be fine, as long as you really use a dark color to show where your actual feasible region is at the end. And in this case, it's just this little mini area right in here. There's still infinitely many points in there, but most of them are decimally. But that would be our feasible region, the spot where all the ordered pairs are located that solve all 3 inequalities.